Now let's move on to see the aircraft composition again as a system. So we have seen before that it includes basically a few systems, like for example the energetic system, the lifting system, the target system, which is why the aircraft is designed, and the protective systems and so on. So now we'll get a little bit close and personal with the aircraft itself and see its composition in a little more detailed classification of the systems by themselves. And the airframe itself is going to be divided into some subsystems and so on. So despite all aircraft systems are interrelated and form a single framework that works all together in order to ensure a seamless operation of the aircraft, due to their high complexity, it is more convenient to decompose them into systems and subsystems, and subsequently grouping them again according to their function, right? So the function of every system is going to locate it into a large classification of all of the airframe and the systems on board. So for example, we have the fuel system, the air conditioning system, the life support system, the control system. So all of these systems, they are incredibly large by themselves, and they include a lot of subsystems and parts and units and so on. So according to the function of every part, we're going to say that this part belongs to, for example, the fuel system, or belongs to the air conditioning system. So let's see shortly the big picture, and then we're going to move from the general picture towards the more detailed picture of aircraft composition. So for instance, we can start with the empty aircraft. So if we remove the payload and the equipment, and that includes, for example, the fuel, the payload, the crew, the system. So if we remove everything that is serviceable each time the aircraft is ready to take off, all of these things taken away, leaves us with the empty aircraft concept, which means that only what is left is the structure, so the airframe, the metal, the systems that are not removable all the time, so that are present during the entire aircraft operation or during the entire aircraft's life cycle, like for example the control system or some basic systems that are not interchangeable during each time the aircraft takes off, and the engines, right? So this is basically what we call the empty aircraft. And also when we talk about the empty aircraft, there is a concept called the dry weight. The dry weight means that the weight of the aircraft without the payload and the fuel and all of those things that are going to be interchangeable each time the aircraft makes a new flight. And all of these together, they give us the aircraft's total weight, right? So the empty aircraft plus the payload plus the equipment gives us the total load of the aircraft, or the takeoff load of the aircraft. Now, a little bit more detailed picture looks a little bit like this. So the empty plane itself, as you can see, includes the airframe, which is the middle, which includes the wing, the fuselage, the tail, the landing gear, the control system. So everything that is metallic belongs to the airframe, right? So, and why it belongs to the airframe, the blue system there, why it belongs to the airframe? Because it performs the function of taking the structural loadings, right? And that's why we group the systems according to the function inside of bigger systems, and which they themselves become part of the empty plane. The power plant, as you can see, it includes the engine, the air intake, the nozzles, the engine control system, the fuel system, and fire prevention system. That's also part of the engine system, part of the power plant. There's some energetic system, and there are quite a lot of liquids there, or oil system inside of the engine. So it's quite a very big system in by itself, the red one. And the systems and equipments that include the avionics and the electric system, navigation system, energy systems, life support systems, and some of the testing equipment and so on. So all of these give us the empty plane, right? So it's part of the empty plane. And the full load includes the fuel, the payload, the crew, and passenger. And again, the criterion by which we can say whether some system indeed belongs to the empty plane or it belongs to the full load, it's whether it changes every time the aircraft takes off. So for example, every time the aircraft takes off, we need to refuel it. We need to add some fuel, right? So this part is clearly not a part of the aircraft itself. So it is just a part that is needed for performing a certain flight. And after that, it can be taken out of the empty plane, right? And also payload. So payload obviously changes all the time. The crew and passengers also they change over time, right? While the empty plane is the plane itself, or it is something that is designed, manufactured, and it doesn't change during the entire life cycle of the airplane. Moving along, so constituents of airframe structure as a system. So now the airframe itself, right? So now the middle itself, the skeleton, the structure itself that is designed to take the loadings. constituted from parts. So before that, system design is actually a solution of technical problem for a constituent part in the general context of the whole. So we move from the general context and then we divide it into smaller systems and smaller systems, so that to simplify and also to allow us to assemble, right? So if we, for example, when we start design, we start from the general and we move to the constituents, while the manufacturing starts a little bit in the opposite way. We take some smaller parts, we assemble them into bigger units, and then we assemble them into some even larger units, and then some global units like the wing, for example, or fuselage, and then we assemble everything in the final assembly line and gets the airframe. So the assembly process starts from the bottom and to up, while the design process starts with the geometry of the airframe. So it starts from the outer geometry, taking into account the aerodynamics. We're going to see what is this a little bit later today. And we go a little deeper, right? So here, as you can see, the airframe can be divided, for instance, into large units which perform a global function inside of the aircraft, like for example, the fuselage, the wing, which is needed to take the fuselage houses, the systems and the payload, while the wing generates lift. So it is kind of a big, large unit that performs a global function inside the aircraft itself, right? The empennage or the tail group, the landing gear, the control system. So these are basically the main 5 units of the airframe, right? And then each unit, for example, the wing, which is just an example shown here. In fact, each of these units can be divided into pretty much thousands of subunits, subsystems, and parts. So the wing, for example, can be divided to include the skin and stringers, the spars, the ribs, the webs, some fasteners, joining elements between the structural elements. So all of these are subunits of the wing, right? And in fact, when we design the structural documentation of every of these parts, we're going to have a number, right? And when, for example, the manufacturing works, the workers take the number of these parts, and by looking at the number, you can see that it belongs, for example, to the wing, right? So which is very important, because if you have an aircraft which is a puzzle of, for example, 10,000 or even more than that parts, small parts, which are grouped into bigger parts and so on. So we have a classification system in order to identify which part belongs to which unit and so on. I think we're going to see this also in some subsequent courses and lectures. Now, now let's see the aircraft's classification according to their flight principles, to see the place of the airplane itself in a little bit general context of other flying vehicles. So we see why an airplane, for example, is such a good thing or such a good flying vehicle as compared, for example, to other flying vehicles that use a little bit different flight principles, like, for example, balloons, ziplines, missiles, rockets. That was completely different type of flight principles. You can see the reactive flight principle. So we have to see what is really the reason why airplane flies and what differentiates it from other flying vehicles according to the flight principle, right? So first of all, a flight principle is, again, the law of nature, or the basic physics of the world that allows us to perform flight, to overcome gravity, right? So if we start with this classification here, for example, the aerodynamic flight force, the lifting force which overcomes gravity, is generated by the air moving around a lifting surface, right? That's why it's called aerodynamic. So aerodynamic means the air, which I suppose comes from the Greek word that means the air, right? Which is the gases that belong to our atmosphere, right? So aerodynamic means that the air is moving at certain speed. So either the aircraft itself needs to be moving at a certain speed, or for example, the wing, if it is a rotary wing, we're going to see this in the next slide, has to be moving at certain speed in order to overcome the gravity, in order to generate a lift force, right? So a lift force is opposite to gravity. And other flight principles include, for example, the buoyancy flight principle, which is basically floating in the atmosphere, right, using some lighter than air gas. So the aircraft is lighter than air, while in the aerodynamic flight principle, as we have said before, the airplane is heavier than air, right? So this is the basic difference between these two principles. But the buoyancy, you need to have an aircraft that is lighter than air, right? And why it is lighter? Because there is a gas that is inside of the aircraft that is a lighter than air gas, right? And Archimedes' force pushes lighter gases above the heavy gases, right? That's why the aircraft floats, like for example, balloon or zeppelin, floats into the atmosphere because it is lighter than air, right? And finally, we have the reactive flight principle, where basically the lifting force is generated by a jet stream downward, which overcomes the force of gravity. So the third law of Newton, which says for every action there is an equal and opposite reaction, plays out. That's why it's called the reactive flight principle. So here the jet stream needs to be extremely powerful to overcome gravity. So by itself, without using air or without using any kind of other type of gases. So only the engine itself generates enough power in order to overcome the gravity, right? And here, of course, the missiles and pretty much every spacecraft is launched using pretty much this principle. Now, if we can see some examples, for example, aircraft with aerodynamic flight principles. So here we can see the airplane in the big picture. So how it is different, for example, from other aircraft that use the buoyancy flight principle and that use the reactive flight principle, right? So the basic thing has been said before of these flying vehicles is that they have to be moving at certain speed so that the dynamic of the air is applied, the aerodynamic principles. So that's how the lift is generated. And as you can see, for example, the aircraft and the glider, they need to have a certain lifting surface, or the wing, right? So they have to be a large lifting surface that generates the lift, and as a result of the aircraft's movement at certain speed, right? Or, for example, the case of the helicopter, which is called a rotary wing, as opposed to a fixed wing aircraft. So the airplane and the glider are here, in this case, a fixed wing aircraft, right? So this is called a fixed wing aircraft, while the helicopter, which is a rotorcraft or a rotary wing aircraft, also called. So here we have a smaller wing which rotates at very high speeds, and therefore the aerodynamic lift principle is also the same, is generated the same. While here we have, for example, the case of the balloon, the gas that is lighter than the air, in fact, it is the air itself being heated up, right? So if we increase the temperature of the gas, its density decreases, right? And using this law of nature, the balloon is able to fly. It's in fact is able to float, right? So the heated air inside of the balloon is lighter than the air outside the balloon, especially at altitude, where the higher you go, the colder the atmosphere gets. So the balloon is able to float easier at higher altitudes because it's colder there, right? And the Zeppelin here, which is basically also uses the same principle, but here we have another gas, which is either, for example, hydrogen or helium. And because hydrogen and helium are lighter than air, so the Zeppelin is also able to float above the heavier gases of the atmosphere. Hydrogen is, by the way, the lightest gas in nature, and therefore it provides the best opportunity to float. Nonetheless, it is flammable, so helium is a little bit better in that regard. And if we compare, for example, these two different types of flying vehicles, one thing we can notice is that the size itself of the payload as compared to the size of the aircraft. As you can see here, the Zeppelin size as compared to a very tiny capsule where the people are housed, or for example, the size of the balloon. The balloon is very huge, while the payload is the small basket where the people are housed. So it is extremely inefficient, right? So that's what we can say for now. It's very inefficient. So we need a very large aircraft to take a very tiny amount of payload, right? And this is the first thing. And the second thing is that these guys depend a lot on the weather conditions, so they cannot fly all the time, while the airplane is pretty much the most sustainable type of flying vehicles that can fly pretty much in every weather and day and night and so on. So it doesn't depend quite a lot on the weather. And finally is the flight speed, right? So these guys are extremely slow because, in fact, they don't fly, they only float. So the only thing that they can do is that they can raise above the atmosphere, but they cannot fly at high speeds like here. While here we have a streamlined shape of the aircraft, so the shape itself is streamlined. Here we have, for example, just a big, you can say, formless kind of balloon, where here we have a streamlined shape because they need in order to be able to cruise at certain speed with a minimum drag, right? And so given the flight speed here is much larger than here, then of course this type of vehicle is much more useful in terms of transporting something from point A to point B and performing some other tasks of the airplane. That includes air transportation, and apart from that, like for example rescue in the case of a helicopter, or also transport, combat, recreational, other functions, you name it. So It is a very useful type of flying vehicle. Why? Again, because it doesn't depend on the weather, and also it flies incredibly fast, right? Because it needs to go faster in order to generate lift, and that lift is sustainable in every kind of weather, right? So it's very important. And finally, if we compare the airplanes with these guys, the reactive flight principle flying vehicles, here the power generated is very big. It's big enough in order to overcome the gravity and even deliver something to space at amazing speeds, like for example, few or many times the speed of sound. However, the problem of this principle is that it's also extremely inefficient. So it is large. The thrust is very large, but it's very short-lived. So, for example, the rocket launcher shown here, it can deliver things to space, but the entire fuel load is consumed in under 8 minutes, right? So it's only 10 minutes. It can fly for 10 minutes, and that's it, right? And the same applies for the missile. Here, the cruise missile is a little bit more efficient because it uses kind of hybrid. It has wings, so it can fly for a little bit longer distances, but it's not a purely a missile, so it is pretty much an airplane. While the reactive flight principle, like the missiles and rocket launchers, are extremely short-lived, right? So they live only for a few seconds, or for like the case of the missile, it consumes all of its energy on board in, for example, less than a minute or a few minutes, or somewhat around that. The rocket launcher is also, although it's very big, like few hundred tons, in fact, of loading of fuel is consumed in less than 8 minutes or 10 minutes, or let's say 20 minutes. And that's basically it. So it's not a sustainable way to fly. It can deliver you to space, it can deliver you to orbit, and that's basically the end of the story. So if you want to fly regularly on a daily basis, day and night, no matter what the weather is, there's only one way to do that, using the aerodynamic flight principle. And that's why 90%, or a little bit larger than that, in fact 95% of everything that flies uses pretty much an aerodynamic flight principle, right? And in this regard, also, if we compare different types here, for example, why the airplane is the most common type of flying vehicles, because it has an unlimited, pretty much unlimited, of course, loading capacity, right? So, for example, if the helicopter, or let's say the glider, is only pure recreational aircraft, that in fact it doesn't fly, it only falls very slowly. While the airplane, because it has an engine, it can fly for a sustainable amount of time and taking pretty much unlimited type of payloads. If the aircraft is large enough, it can take a few hundred tons, let's say, of payload, which is very large, and it can travel pretty much up to 22,000 kilometers, which is pretty much the entire planet, if you like, Earth. So it's a very efficient way to fly. And therefore, let's see the aerodynamic flight principle itself, how it works, and why it is so efficient. So we have seen the definition of the airplane before. So it is a heavier than air flying vehicle with an aerodynamic flight principle, as opposed to other flying vehicles which are a little bit lighter than air. And for generating lift, we need a wing, a tail, and we need, in order to take a driving force, we need a power plant or propulsion system.